We're given the Solow model without population growth and without technological progress, where we're given the Cobb-Douglas production function y is equal to L1 minus alpha k alpha. So we're given that investments are equal to savings is equal to SY because we're assuming a closed economy and no government. And then we're given a capital accumulation equation, K dot is I minus delta K. So what you want to do is, in the Solow model, we want to derive the dynamic equation. And when we talk about the dynamic equation, the goal is that you want to derive an expression for K dot, which is change in capital with respect to time, as a function of capital per work, which is change in capital per worker with respect to time. And you want to derive this expression for K dot as a function of capital per worker I small k and parameters of our model. So you want to reduce everything in terms of small k. So we essentially want to find k dot as a function of small k. This is our dynamic equation, where we want to express k dot, change in capital per worker with respect to time, as a function of capital per worker and only parameters of the model. Right, and since here we're looking at the Solow model without technological progress, so we will do all of our analysis in per worker terms. If we had labor augmenting technological progress, only in that case do we do analysis in per effective worker terms. So to achieve this goal, to find k dot as a function of k, the first thing we do is we start with the definition of small k, I capital per worker, that is small k is equal to capital by L. So now what we do is, so since the goal is that you want to find k dot, right? So we start with the definition of k, and to find k dot, what we're going to do is we're going to now take natural logs and time derivative on both sides. Because remember, the growth rate in continuous time for a variable y is y dot by y, which is just the time derivative natural log of y. So in order to get there, what we're going to do is, because remember we talked about this, the growth rate in continuous time is y dot by y, which is d by dt ln y. So what we're going to do is we start with the definition of k, then we take a natural log and time derivative on both sides in order to write it in terms of growth rate. So when I take natural log on both sides, this becomes ln k is ln k by l. And then using log properties, we know ln capital K by L can be written as ln capital K minus ln L. Here keep in mind, capital K is aggregate capital stock and small k is capital per work. So now we take time derivative on both sides. We differentiate both sides with respect to t. So we have this. So now when I take the derivative of ln small k with respect to t, we know this is going to become 1 by small k times the derivative of k with respect to t. Because remember, we're taking the derivative of ln k. So first it's going to be 1 by k, then the derivative of the inside with respect to t. Similarly here, when we do it, it's going to become 1 by capital K, the derivative of inside, I capital K with respect to t. Similarly, over here, it's going to be 1 by L into derivative of the inside with respect to t. So now we know K, we use dot notation to denote the derivative of a variable with respect to time. So dk by dt is just K dot, because that's just notation, how we've defined it, that the dot over a variable denotes its derivative with respect to time. So this d capital K by dt can be written as capital K dot, dl by dt can be written as L dot. Now from here, what we do is, make K dot the subject by multiplying both sides with small k, because remember, the goal is to derive an expression for K dot, right? So we started off with small k is equal to capital K by L. From here, we took natural log and time derivative to get it in growth rate form, which gives us k dot by k. Now we just multiply both sides with small k. Right now, what we do is, now this small k over here, we write it as capital K by L, and this L dot by L is just equal to N. Because oh sorry, so this was not the case of, so this is just the Solow model with population growth, but without technological progress. Sorry, my bad. So this is not without population growth, so this is with population growth case we're looking at. So L dot by L is N. If this was without population growth, then L dot by L would just be equal to 0, right? So here the Solow model we're looking at is the Solow model with population growth and without technological progress. Right, so over here, L dot by L is N. If you are looking at without population growth, then L dot by L would just be 0. It doesn't really matter. That's just a special case of this. Right, so then what we do is, so then this becomes, so we write small k as capital K by L and L dot by Ln. If this was without population growth, then N would just be 0. Right, so it doesn't make a difference. We're just looking at a more generalized case where we do have population. So now the issue over here is, now we do have an expression for K dot. Remember, the goal was that we wanted to find an expression for K dot, but we wanted that expression as a function of small k. And here notice this is capital K, but we're looking for dynamics of small k. Right, this is capital K. Right? We don't want this capital K here. Remember, we want to express K dot as a function of small k. Here we do have small k and parameters of the model. But here the issue is that we have a capital K, but we're looking for the dynamics of small k. We don't want this capital K here. We want to express small k dot as a function of only small k. So we need to substitute away this capital K dot. Right, so using the capital accumulation equation, K dot is I minus delta K, where I is Sy. So we're going to use this to substitute away this capital K dot by L in 1. Because remember, the goal is to find the dynamics of small k. We want to see how we want to find the dynamics of small k. We want to express K dot as a function of small k. So we want to substitute this term away. And for this, we'll use a capital accumulation equation. So then what I can do is this y, we can substitute to the production function L1 minus alpha k alpha, because when we write y, because here we get y in terms of capital K, and then we'll divide both sides by L and get it in terms of small k. So now what we're going to do is we're going to divide both sides by L. When we divide both sides by L, so what we're doing is this becomes capital K dot by L is equal to S. This is y by L. So this is just output per worker. So this is our per worker production function, right? Minus delta capital K by L. This capital K by L is just small k. And this is just y by L. So this is just y by L. So this is just a per worker production function K alpha. So now what we do is we now have this capital K dot by L, right? So now we have this capital K dot by L, which is solely written in terms of, so now this is a capital K dot by L. Now this is only in terms of small k and parameters of the model. So what we can do is now we can substitute the capital K dot by L that we had in 1. We did not want this here. We wanted K dot only as a function of small k and parameters of the model. So we can substitute this capital K dot by L with this expression that we found from our capital accumulation equation. Right, so this was, so here we have K dot. So this is capital K dot by L in 1, which we substituted with this over here. The expression that we found from our capital accumulation equation. And from here, then we can write K dot as Sk alpha minus delta plus Nk. This is giving us our dynamic equation in per worker terms. We have expressed small k dot solely as a function of small k and parameters of the model S delta and N. So we found a dynamic equation of the Solow growth model.